Okay, and so the mathematical statement that we're going to want to prove in this video will be the following. So, suppose we have a graph G, which, as a reminder, is a tuple of vertices and edges, and let G be a simple graph. And so, just a reminder, what we mean by simple graph is that it has no self loops and no multi edges. Okay, so basically what this means is that there isn't a vertex that has a self loop, and there aren't any two vertices that have multiple edges between themselves. Okay, so that's what that means. And so we're saying we have a simple graph with at least two vertices, and now the claim is that there exists two vertices, okay, UV in the set of vertices with the same degree, okay? And then just a reminder, what does degree mean? Degree of a vertex is number of incident edges. The number of incident edges into that vertex. Okay, so for example, if I have, let's say, a graph like this, let's do this like this, okay, and we count some of its degrees. So let's first label the vertices, okay, and so the degree of vertex A is, well, let's see, it has this edge and this edge, right? So degree of A is equal to 2, okay? And then similarly, the degree of B is equal to 2. Let's find another one. Let's see, this guy, the degree of F, it has 3 incident edges, and so its degree is equal to 3, right? And this is the notation that I'll use. Degree deg of F is just the degree of that vertex. Okay. Okay, and so now, like any mathematical statement, you always want to sort of get a feel of what exactly it's saying, right? So, what is this saying, right? What is this saying? Okay. Well, let's look at an example. I guess we kind of already have an example. So let's first look at this one, right? So what this is saying is, you have this graph, right? This is some graph G. It definitely has at least two vertices. Now, what the statement is saying is that there are at least two vertices with the same degree. And so we see that this is definitely true in this case, right? We can look at, say, vertex A and vertex B, and we notice immediately that the degree of A is 2 and the degree of B is 2. And so A and B are two vertices with the same degree. If we try to think of another graph, which might not be connected, right? So it's possible. So here, there isn't in the statement here, there's no claim about G being connected, right? And so what that means is that you could have, say, a singleton vertex here, right? So let's call this A. Then maybe you have this vertex B, which is connected to the vertex C, and then this creates a whole big graph here. And let's see. So the degree of A is 0, right? Because it has no incident edges. The degree of B is 1 because it has one incident edge. The degree of C is 3. But then the degree of these three guys is 2, right? So the degree of this is 2, the degree of this is 2, the degree of this is 2. And so altogether, we have 3 vertices that have the same degree, okay? Of course, showing you examples does not consist in a proof of the statement. This is just to sort of give you an intuition of what exactly the statement is talking about, right? And examples are always good when you have absolutely no idea what the statement is saying. They help you really understand, first of all, what you're trying to prove. And sometimes they allow you to get some intuition as to why something might be true. Okay. So in this case, I mostly just use this examples to illustrate what the statement was saying. Now we actually need to prove this, right? So we need to prove this. So let me write proof. And so the proof is actually going to begin, well, okay, let's see. I'll give you the intuition of what the proof is. So the intuition is that there's a finite number degrees that can be assigned to vertices, right? So vertices can be assigned to a finite set, let's say, finite set of degrees. Okay, so what I mean by that is, so that is, if I have a graph G vertex set size n, right? Suppose n is a natural number. It has to be a natural number because n represents the number of vertices of the graph. Um, of course, n must be finite because we're not dealing with infinite graphs, okay? And I know that n is greater or equal to 2, right? So I have n vertices, right? Now, what are possible degrees that my graph can have? Well, that the vertices of my graph. Well, let's think about it, right? We can definitely, like, what's the smallest degree that a vertex can have? Well, we can see here, right, that it's 0. So a vertex could have no incident edges, and so its smallest possible degree, right? So if we have possible degrees, then the smallest possible degree that a vertex could have is 0, right? Then it could have degree 1, like this vertex has here. It could have degree 2. And then what's the largest number of incident edges a vertex can have? Well, because we're considering no self loops and no multi edges, right? There is a maximum number, okay? And it might seem unintuitive at first because some of you might immediately say, oh, it must be n. Well, in fact, the maximum degree of any vertex in a graph with n vertices is n minus 1, right? So why n minus 1, right? Why n minus 1? Well, consider the vertex. Consider the vertex connected to all other vertices, right? So suppose you have n vertices, right? And you have one vertex that's connected to all of them, okay? Well, it's going to be connected to how many vertices? Because there are n vertices in total, the number of vertices that this guy is connected to is going to be n minus 1. Minus 1 because it's not connected to itself, okay? And so the maximum degree that a vertex can have in a graph, in a simple graph of size n, is n minus 1. Okay, so that's the setup. And now what I want you to think about, right, is that there's a reason why this example is right after the pigeonhole principle. And that's because you can think of the vertices as the pigeons, okay, and the degrees as the pigeon holes. Okay, and so what does that actually look like? Well, if we add a page here, what that'll look like is the following. So, um, right, supposing again, I have this graph, this simple graph with n vertices, at least two vertices, then the possible bins or pigeonholes or degrees that I can have are 0, right? 1, 2, all the way to n minus 1. Okay, so these are my pigeonholes, right? My pigeonholes are equivalent to the possible degrees of the vertices in G. Now, how many possible degrees are there, right? How many pigeonholes are there? Pigeonholes are there? Well, there's 0 is 1 is the second one, 2 is a third one, n minus 1 will be the nth possible degree, right? So this is just, you just have to notice that um, if you start assigning bins from 0 all the way to n minus 1, you end up getting n possible bins, right? And so when I say bin, that's equivalent to pigeonhole, which is equivalent to what we actually care about, which is the possible degrees of the vertices in G, okay? And so if you enumerate a sequence from 0 to, let's say, 3, you're going to end up with 1, 2, 3, 4 elements, okay? And so if you have 0, 1, 2, all the way to n minus 1 degrees, right, then you end up with n possible degrees, okay? Right? So again, remember the vertices are the pigeonholes. Now, what are the pigeons, right? So how many pigeons are there? Okay. Remember, what are the pigeons? The pigeons here are the vertices, and the pigeonholes are the possible degrees. Okay. Well, in this case, I've stated that I have n possible vertices, right? So there are n pigeons. Aha, I see. But what you'll notice, okay, is that I have n pigeons and n possible degrees. And so at this point, and you need to make sure you understand this, is that at this point, it would be incorrect to apply the pigeonhole principle. Okay, it would be incorrect because the pigeonhole principle tells me that if I have n plus 1 pigeons and n pigeonholes, then there's going to be a pigeonhole with at least 2 pigeons. But that's not what I have in this situation, right? I have n pigeons, n pigeon holes, right? So I still need to reduce, or in fact, what you need to think about now is there a way for me to rule out a pigeonhole so that I can have, say, n pigeons and n minus 1 pigeonholes, right? And so the trick here is I want to try to make this look like an instance of the pigeonhole principle, right? I.e., what I would like to have is I would like to have n pigeons and n minus 1 pigeonholes. Okay? Now, why n and n minus 1? Because I can't have more or less pigeons because these are the vertices. I can't change the number of vertices that I have because those are just the vertices in my graph. But maybe I can use an additional argument about graphs to reduce the set of possible degrees or the set of pigeonholes that can be assigned to the pigeons or that can be assigned to the vertices. Okay? So that's the additional intuition that you have to, or the additional sort of direction that you need to think of when you're doing something like this. Okay? And so how do I do that? Well, I have to make the not so obvious observation that in a graph G, right, where the vertex at size is greater or equal to 2, and I'm saying that this is equal to n, right? So in a graph G with n greater or equal to 2 vertices, there cannot be both a vertex of degree 0 and a vertex of degree n minus 1. Okay, this is the additional crucial observation, I would say. So this is the crucial observation that's going to allow us to use the pigeonhole principle. And so what is this observation saying? It's saying, essentially, if I have a vertex of degree 0, I cannot have a vertex of degree n minus 1. Why? Because if I have a vertex of degree 0, that means that the vertex of degree 0 is not connected to the rest of the graph, right? And so there can't be a vertex of degree n minus 1 because that would mean that it would be connected to all the other vertices. And so similarly, it's a very symmetric argument, right? I cannot have a vertex of degree 0 if I have a vertex of degree n minus 1, because that would mean that the vertex of degree n minus 1 is connected to all the other vertices. And so the vertex of degree 0 cannot have degree 0. Okay? And so what that means, right? Therefore, means that there are only, let's change color here, n minus 1 possible degrees to choose from, right? There are only n minus 1 possible degrees because in this enumeration here, either this bin is empty or this bin is empty, right? Because both cannot be non-empty at the same time, right? So if this bin is non-empty, right, then this bin must be empty and vice versa, right? So that just tells us that these two bins, these two degrees, right? These two degrees, 0 and n minus 1, cannot both have vertices assigned to them at the same time for any graph, okay? And so that means that I can either choose from vertices 1 to n minus 1, or degrees 1 to n minus 1, or degrees 0 to, say, n minus 2, okay? Right, I can't have both 0 and n minus 1, okay? And so now that tells me that in fact I only have n minus 1 possible degrees to choose from, or in other words, I only have n minus 1 possible pigeonholes to assign my pigeons to, okay? And so we can conclude Oh, we can conclude the proof then by saying, therefore, by the pigeonhole principle, there must be a degree that is assigned to at least two vertices in G. Okay, and so therefore, because G was picked arbitrarily, right? I had put no constraints were placed on G. It was just some arbitrary graph with some vertex set size n that's greater or equal to 2. And so because G was picked arbitrarily, this implies that for any graph G, right, there exists at least two vertices with the same degree, right? And that concludes our proof. So we can put a box and then fill it up, or you can just put a box and not fill it up, or you don't have to do anything, right? But this essentially is how you would prove this initial statement, okay? And that's essentially an application of the pigeonhole principle. Okay, so hopefully that's clear. This concludes our video on describing the pigeonhole principle and then applying it to a given example.